Most of us have seen the rainbow-hued breakdown of the composition of light. Light, of course, is a form of energy. A magnetic field changes the behavior of light, a phenomenon known as the Zeeman effect. The Zeeman effect occurs when a spectral line, one of those little lines you see in a rainbow band of light, is split into varying frequencies as light enters a magnetic field. Dutch physicist Peter Zeeman made his namesake discovery in the late 1800s. He noticed that powerful magnetic currents would widen the convergences of units of sodium under intense heat. Further analysis demonstrated the extension was a clear separation of spectral lines into more than a dozen entities. The Zeeman effect has assisted physicists in verifying the energy levels in atoms and categorizing their mass and spin. It's also a useful way to evaluate atomic particles and electron paramagnetic resonance, and is essential in nuclear magnetic resonance spectroscopy. Classically, an electron of mass me and charge E orbiting the nucleus is described as a tiny current loop that produces a magnetic dipole moment mu, which is proportional to its orbital angular momentum L. In the presence of a magnetic field B, the dipole experiences a torque due to the Lorentz force. This slightly changes the orbit, resulting in the energy shift for the electron. So when we add the magnetic field, we get torque, which changes the shift. This model, which explains the Zeeman splitting in terms of transitions between levels with different values of L in the magnetic field, ignoring the spin angular momentum of the electron, is rarely observed. Nevertheless, this model captures the essence of the physics underlying the effect. And again, you can see where it fits in the equation and how we can solve for delta E. Zeeman-Lorentz model for transitions between states with L level 2 and level 1, when there is no magnetic field, or B equals 0, there's a single spectral line, the green one. When we induce or have the electric field, the magnetic field, there are two additional spectral lines for a total of 3 lines. You will have your green, you will have a red, and you will also see a purple. Another way to look at this is that our spectral lines, when we have no magnetic field, we see a single spectral line. When we induce a magnetic field, we then see 3 spectral lines. And this is for the same atom. Now, how this works with NMR. The magnetic moment, mu, is a vector quantity that has both magnitude and direction. In the absence of an external magnetic field, the magnetic moments, mu, are randomly oriented. So the electrons are moving in all different directions with different spins. But what happens when we add a strong external magnetic field? The first thing we have to look at is the induction of our magnetic field. So B sub naught. It exerts torque on angular momentum L and causes nuclear precession, which is analogous to precession of a spinning top. And you can see what the spin looks like here. The frequency of the precession, often called the Larmor frequency, is proportional to the gyromagnetic rotation and the strength of the magnetic field. So there's the equation that shows us how the NMR works. In the macroscopic world, the two magnets can be aligned in an infinite number of orientations. At the atomic level, these alignments are quantized, and the number of orientations, or spin states, are equal to 2I plus 1. We will only deal with spin 1/2 in 2 states. So once we add the magnetic field, everything lines up, either up or down when we look at the arrow, so one of the 2 states. The different quantized orientations will each have an energy level determined by the Zeeman splitting. And we can see here, as we add the magnetic field, the splitting occurs. And we see either the positive spin or the negative spin. And you can see when we add these up, the positive spin minus the negative spin, we see the change in energy. Knowing the change in energy, we can stimulate the transition between these two states by applying an RF field such that this occurs. In NMR spectroscopy, we are going to perturb the spin states by stimulating transitions between the energy levels. And again, you can see the math here. That's only off by positive half and negative 1/2 based on the different spinning that we see. Now, how a spectrometer works. The first thing you do is you need to get this superconducting magnet that generates a powerful magnetic field that is tens of thousands of times stronger than the Earth's magnetic field. Samples are placed in and exposed to radio waves. The spectrometer transmits and receives the waves to make the NMR measurements. And of course you have a computer that does all the data processing.